Or recording is started. We are on mute.
Okay, I see close to 25 participants here, so I guess we'll start here. Good morning, everyone. My name is Ripu Bhanjan Singh, and I manage the monitoring, evaluation, learning, and knowledge management piece for Greening the Grid program. It's my pleasure today to welcome you all to the first webinar of the GTG webinar series, which is in collaboration with the Asia-led partnership. This webinar series is intended to share the results and lessons from the GTG RISE initiative. GTG Greening the Grid is a joint initiative between Ministry of Power, Government of India, and the United States Agency for International Development, which is to manage the large-scale integration and renewable energy into the Indian power grid. The central component of the GTG is the renewable integration and sustainable energy, which is the RISE initiative, and which involves the design, implementation, and scaling up of a series of prioritized innovation pilots, including the one on flexible operation of coal-based power plants that support the integration of RE into the grid. Today I see there are participants from different parts of the world here. We sincerely appreciate you all getting on the call and making it to the event. We hope that you benefit from the session, and we look forward to your continued cooperation and participation and feedbacks as well, so that we can improve upon the next webinar into the series. Just to give you a little brief about the structure of the event, we will have a brief introduction to the GTG program by Monali Hazra, who is the Clean Energy Specialist at Clean Energy and Environmental Office, CLEO, at USAID India. This will be followed by an overview of the pilot on flexible power generation under RISE initiative by my colleague, Mr. Anuj Bashisht, who is the pilot manager for the pilot. And finally, we will have a detailed presentation by our special international speaker, Mr. Nikhil Kumar, who heads the Power Grid Division at Intratech and is also the technical partner of the study conducted under the initiative. Towards the end, participants will have the opportunity to ask questions and get answers from the eminent speakers we have. With that said, yes, we do have an senior advisor with us from NTPC, Mr. Anjan Kumar Sinha as well, to answer any queries from an operational standpoint with the given experience he has, about 25 to 30 years within NTPC. I think with that said, I'll invite Ms. Monali to give a brief overview of the program Greening the Grid, and we look forward from there. Once again, thank you, and we welcome you on board.
Thank you, Ripu. Welcome to all for this first webinar conducted under USAID's Greening the Grid program. So as Ripu just mentioned, Greening the Grid is a bilateral program between USAID and the Government of India, Ministry of Power, with the objective being to support the Government of India's initiatives or efforts towards managing large-scale grid integration issues. The Greening the Grid is a key initiative under USAID's Asia Edge, which stands for Enhancing Development and Growth Through Energy, which basically focuses on enhancing energy security in South Asia. So Greening the Grid program was started almost 3 years back, and it goes on till 2020. It has various components, 4 components. The first one focuses a lot on modeling and power system reforms. Under this piece, USAID had supported the national grid integration and 2 regional grid integration studies that were conducted by USAID's US National Renewable Energy Lab along with POSICO. The study had come out with various recommendations and some of the key findings. One of the key findings was obviously that in order to achieve India's 175 gigawatt of renewable energy target, the coal plants would have to be, made much more flexible or would have to operate flexibly. The second component of the program focuses on the pilots, the grid integration pilots, and it kind of is the core or the heart of the entire Greening the Grid program. The objective of this component was to, validate and demonstrate some of the key technologies and solutions that could support in integrating renewable energy. And it was also that the recommendation that emerged out of the National Grid Integration Studies will be piloted under the GTG RISE initiative. This component is implemented by Deloitte Consulting, and they are the one who are organizing this webinar as well. The third element of the program focuses much on the peer-to-peer partnership. In this case, the key focal group for us is the system operator as well as the regulator. So we have established 2 parallel US-India partnerships, one focusing around system operations, the other focusing around regulatory partnerships. In both the cases, we have 2 US agencies implementing it. Under these 2 initiatives, we have conducted several capacity building workshops, peer-to-peer reviews, site visits to US, and vis-a-vis bringing in system operators from US to come and spend some time in India. So a lot of opportunities to do peer-to-peer exchanges under these 2 components of the program. The program also recognizes the fact that USAID is not the only player in this field. So there's a lot of focus on donor-to-donor coordination. USAID has an MOU with both GIZ and DFID focused around grid integration. There's also a lot of focus on the private sector. We would like to leverage the expertise of the private sector, and towards that, an industry advisory council has been established under the program in partnership with the US ISPF, again to promote exchanges between US and Indian companies and to tap into their expertise towards grid integration issues. In the last, if you can move to the next slide, Anuj. So in the last 3 years, the program has done has already, had made some progress towards these issues. The program is piloting 6 innovation solutions and technology, one of them being the flexible operation of coal-based power plants, and today we are going to discuss more on the findings of that particular pilot. In addition, we also have pilots on battery energy storage system, on automatic generation control on our renewable energy plant, as well as on hydro facilities. There's a pilot on market reforms, there's another pilot on dynamic reactive power compensation. So there are around 6 pilots which are ongoing under the program. There are also 2 white papers which are currently under development. Once completed, another one which focuses on electric vehicle still to be implemented. The program has already leveraged $12.44 million in terms of investments from the partners, whether it is partners such as NTPC or Power Grid Corporation, and so on and so forth. We have around 19 members on the Industry Advisory Council. The program is also providing regulatory supports to states, and 14 states have been supported thus far in terms of coming up or drafting their forecasting and scheduling regulations, as well as TSM regulation. The program is also working with or supporting CRC in its market design. We have trained around 1,472 people thus far, and almost 7 reports have been developed. So that's a quick broad 10,000 training ticket program, and I'll pass it on to Anush to talk more in detail about the coal flexibility pilot. Thank you.
Thanks, Monali. Seems that a couple of attendees were not able to hear. Maybe the audio settings they need to change, but I hope the rest of the attendees have been able to hear that out. Good introduction and welcome remarks from Ripu and Monali. What I intend to showcase is the details of the pilot on the coal flexibility that we have been doing. But before that, it would be good if I can just breeze you across to the different pilots that are being taken up under the USAID GTG RISE initiative. So one is, of course, the flexible power generation pilot, under which the first webinar series is on, and this has been implemented with support from Intertech US, and we are supporting NTPC and the Central Generating Utility of India, as well as a state generating utility based out of Gujarat, that's GSECL. In addition to this pilot, we have another 5 pilots. One is, of course, the battery storage systems pilot, where we are actually testing the use cases of battery energy storage deployment in one of the substations of PGCIL at Puducherry. This includes both frequency and voltage use cases being tried and tested out. It's in the advanced stage of deployment, and we will be able to see the results soon. The automatic generation control pilot is apparently being tried out on a couple of hydro plants in Karnataka, the southern state of India, as well as in one of the solar plants of NTPC. There is another pilot on regional platform for reserve sharing, where we are looking at how to share how to create a platform for sharing of ancillary services and creating a national open access registry for smooth data flows information. We have another pilot on dynamic compensation for large solar park. This essentially now has been integrated with the AGC solar pilot at NTPC's solar plant. And there is another pilot that we intend to look at is on the real-time monitoring of rooftop solar. That's essentially the distributed energy rooftop forecasting. That's still being discussed at the pilot stage, but rest of the 5 pilots are in a well advanced stage of deployment. Now, I will quickly take you through what we are looking at in the coal-based flexible power generation with NTPC and GSECL. We started this pilot way back in early 2017, and it's almost 3 years now. If you look at this slide, there have been 4 stages, and we are in the 3rd stage of pilot implementation. We started initially with the techno-economic assessment, comprising of technical due diligence and detailed feasibility assessment of 2 units of NTPC, one 200 megawatt unit at Ramagundam, that's in the southern state of Telangana in India, and 500 megawatt unit at Jhajjar plant, that's a state in North India, in Haryana. The objective of carrying out the technical due diligence studies was to assess the existing state of operations of these units, how these units have run over the past 10 years, what all design components have been incorporated, what all changes have been made to the OEM design, and how it will help in carving out or charting out the flexible roadmap for these units and similar kind of 200 and 500 megawatt units in the country, especially for these two utilities. So that's where we had the international support from our technical consultants, Intertech. Intertech brings in a lot of expertise based on the wide experience they have in conducting similar studies worldwide. And with the help of Intertech, we were able to assess the damage cost modeling studies, and feasibility reports were presented to NTPC as well as GSECL. I should mention that similarly for GSECL, which is generation utility in Gujarat, we conducted a similar study for 200 and 500 megawatt units at their Ukai thermal power station. The next stage included looking at, once we had the damage cost modeling studies with us, we wanted to look at how the flexible operations would result in the additional O&M expenses and the life cycling costs that would occur because of increased cycling in the near future. So that requires, since these are regulated assets, this required a regulatory compensation mechanism. In India, currently we have regulations for technical minimum of power generating plants to be run at 55%. Since we are looking at a future where we might be required to run coal-based plants at say 30% or 40% technical minimum, we may also be looking at scenarios where units would be frequently subjected to ramp up and ramp down on a single day basis, to shifting of units as well. We charted out a compensatory mechanism and have presented the same to the regulator for allowing compensatory mechanisms for such low load operations. We are currently in the third stage of pilot implementation, where we have recently put up a fleet-wide strategy to NTPC for charting out their future course of action for taking up flexible operations in their fleet of 200 and 500 megawatt units. We have, going forward till the year December 2020, we intend to support NTPC and GSECL in taking up, in implementing these identified flexible interventions in the units, including vendor selection of OEMs. And over the period of last 3 years, we have been conducting various workshops, and there have been executive exchange with US and India under the USAID Utilities Exchange Program, as Monali mentioned. So I look forward to a detailed presentation on the flexing practices in India as well as abroad. And this is one of the first. This is the first webinar, first WebEx event in the series of webinars that we are going to take place in the coming months. Also to mention, since the other pilots are also in an advanced stage, we also plan to conduct similar webinar series for the other pilots as well, and we will keep you all posted for that as well. So with that, I will give I'll request Nikhil to start his presentation. Before that, I would like to request all attendees to post their questions on the Q&A chat window. And after the presentation made by Nikhil, we will be taking up the questions one by one, and we have eminent panelists which will be able to discuss out the questions and clarify any of your queries. So Nikhil, over to you. I'll just give you the presentation rights.
Well, thank you, Anuj, Ripu, and Monali. And thank you to all the attendees for joining us as well. It's quite humbling to see what a small part we're playing in the big project. So let me quickly share my screen, and we will get started. All right, Anuj, if you could confirm that you can see my screen.
Yes, I can. Okay.
All right, so let's quickly start with predictions and trends, and I want to go through some of my slides fairly rapidly so we have some time for questions. So I think if you're attending this webinar, you already know the trends. In general, 2010, which is only 9 years ago, we had some amount of wind, predominantly in Europe, China, US, and India. But just fast forward 6 years, and you can see what a big change in wind capacity there has been on throughout the world. So today we have 57 countries out of some 90-some countries that have 100% renewable targets. Renewables are pretty much what dominates new capacity addition. In fact, in 2017, we had more PV capacity added than coal, gas, and nuclear combined worldwide. So a bulk of that addition comes not in Europe or in the US, but primarily in China and India. So in India, if you notice, we went from 13 million kilowatt capacity of wind to 28 million kilowatt capacity just in 6 years, and the targets are quite ambitious going forward. So here are some of the predictions that Intertek has worked on with various other partners. So we did some studies with the GE as well as the PJM system operator and the Department of Energy and the NREL lab in the US. And typically what happens when you add renewables to the grid is that most of the fossil fleet, the conventional fleet, has to change its operating profile. So some of the scenarios and analysis that we did in the past suggested that operating costs for conventional fossil plants would increase by 2 to 5% on average. And as markets have evolved, or you are in a regulatory world, 2 to 5% increase in operating costs can have a big impact on your revenues. So we think that's a big deal. Also, if you think about it, if you have a coal-heavy generating profile or gas-heavy generating profile, what happens is that as you add more renewables, they will displace the units on the margin or even units that are traditionally base-loaded. So if you looked at the Western grid in the US, which is gas-dominated, so you have a lot more gas than coal units, as you added 4 megawatt hours of renewable generation, you displace 3 megawatt hours of gas from the grid. So not only do you have increasing O&M costs, 2 to 5% increase, you also have reduced revenue from not being able to generate. And finally, when we look at a system-wide level, we found out that there was additional cost of around $500 million annually in production costs associated with increased cycling operation. So clearly, at least from a US standpoint, there are significant cost impacts as you perform flexible generation. So as Anuj mentioned, one of the outputs of our analysis for the GTG program is to assess how capable are the coal units in India, both at GSECL and NTPC, to perform cyclic operation, as well as what is the impact in terms of financial, O&M, and reliability of the unit. So if you cycle the unit today, what happens tomorrow as you have to spend more money on the units? And so here's very briefly, I'm not going to go through it in a lot of detail. These are various markets in the US, and what this chart is showing you is the frequency of negative prices. So not only do you have less generation, you also have negative price signals in the market. So that makes things even worse if you're a conventional fossil unit as you add more renewables on the grid. And one thing to point out is that it depends on which market you're in. So if you're in California ISO, you can see as the penetration of wind goes up, the negative price share also goes up. But on the flip side, if you're in PJM or MISO, which are other markets, that frequency isn't that dominant. So there are certain, there are certain regions which are affected more than others. So I don't want to say that just because you add renewables that would be the result. And I think I can skip this because it's a U.S. scenario, but something to point out is that if you look at the US, the capacity factor of coal units have gone from 60 and 61% in 2013-14 down to 54% in 2018, with gas being the dominant generation. And so very quickly, what we wanted to see was take a look at how wind and solar impact units' conventional fleets. So we take a look at 3 different regions in the U.S. We take a look at California, Texas, and Iowa. California is a solar-heavy state. They have wind, but solar is a dominant renewable generation technology, along with natural gas. Texas is the largest producer of wind in the U.S., and Iowa, that is in terms of the total amount of wind, and Iowa has over 25% renewables with a largely coal fleet. So Iowa should represent what is likely to happen in India. So when you take a look at these 3 regions, what happens is that, I can skip this, is that here's what happens on the fossil fleet. So on the left-hand side, you're seeing is the California fossil generation. And what we have is offline hours, load following hours, base load operation, and over MCR. So if you're using duct firing on a combined cycle unit or something of that sort. So if you look at California, what happened is that between 2005 and 15, there was a significant increase in units staying offline. Also, what happened was that these units also operated at full load. So because it's a solar-heavy state, the requirements on the conventional fleet is less of low load operation, but more of quick start, because as the sun comes up, you want to shut down the units quickly, and when the sun goes down, you want to turn them on quickly. So you can see that that's exactly what's happened in California. If you look at the rightmost chart in Texas, which has a lot of wind, what happens is that because you've got so much wind, you have to turn off a lot of units. So you can see an increase in offline hours. But other than that, wind has a little bit less of an impact in terms of cyclic operation of on-off. But if you look at Iowa, which is a coal-heavy state with a lot of wind, they have both replaced the coal fleet, so you have a lot more offline hours on the fossil fleet. Also, if you look at this baseload section, where the number of hours on baseload have also reduced. So not only are you not running a lot, you're also running at low loads because you have a coal fleet which is not that flexible. And, you know, this is on the left side is the classic California duck curve. So as the solar comes on, you can see the ramping requirements on the fossil fleet on the left. You can see in Texas very little change over time. This is 24 hours on the x-axis and the amount of energy on the y-axis. But Iowa, you can see that the red line is 2012, the blue line is 2015. You can see throughout the 24 hours, the generation from fossil fleet has reduced. So throughout the 24 hours, wind is displacing the coal units. But when you look at coal units, there's a different scenario if you're a small coal unit or a large coal unit. So if you're a large coal unit, you can see on the chart on the right on the orange line is that there is a slight reduction in capacity factors from 2005 through 15. But if you're a smaller coal unit, which means that you're less efficient, the impact is far more dramatic, where you've gone from 60% capacity factor down to 20% capacity factor. So size matters as far as your coal unit in a renewable world. I think part of what Anuj was mentioning, and I'm hoping Mr. Sinha would add some comments later on, is that there are some opportunities to be made in this type of an operation. So if we have regulatory process of cost recovery and you don't have flexible generation from the coal units, then the incentives are moot. So you need to have system operators be able to get flexibility from the grid. So obviously you have price volatility, you have a higher ancillary service prices. So you should, if you're not flexible, you can't take advantage of some of these incentives that the market or the regulatory process is going to put in place. So that's something you want to be able to do. So here's the problem statement, right? So if you're looking at flexibility, what is important? One is startup time. Another is how low can you operate the unit? Are there any local emissions requirements? So you have to meet emissions compliance. And then what are the ramp rates when you're running at low load going to full load? What does this impact? Number one is safety. We've had concerns pretty much worldwide as you operate units in cyclic mode that there are catastrophic failures of equipment that you did not anticipate because you are used to running base loads. So safety of personnel is paramount. The equipment life is going to change. Reliability is going to change. Costs in terms of maintaining equipment is going to change. And the amount of money that you can make in the market or a regulatory world is going to change. And how do we address some of these impacts? Is one, you make operational adjustments. Two, you invest capital in the units. And three is you determine which part of this first, what is important, is most valuable. Is faster startup time more valuable for you, or is it minimum load that is valuable for you? So you need to understand what is important for your grid strategy versus making your unit, the ultimate flexible machine. And that's not the point of doing a flexibility analysis. So in general, what do we need to do? Is one, as you cycle the unit, there will be an increase in costs, and older fossil units. Even when you look at the Indian case, the Ramagundam unit as well as the Yokai units, they were commissioned in the 1980s, so well past their prime, 25, 30 years of operation, primarily base loaded. So older assets versus they also have the Jhajjar unit, which is relatively new, but has been operating with excessive cycling. So you can have an older unit as well as a newer unit changing their operating profile. And in this case, the power plant has a sad face, not because it's being cycled, but because the dispatcher or the regulatory process is not accounting for the damage that the unit is undergoing. So if it can get compensated for the flexible operation, then maybe the plant's going to be relatively happy. So the first statement I'd like to make is that almost any unit can be cycled. In fact, it can be cycled with absolutely no intervention. You can take an existing unit, a supercritical unit if you'd like, and change its operating mode. Now, what that will do is that you have to account for the increased wear and tear damage. You have to both in terms of long-term penalties. So as you cycle a unit in due course of its time, you will have more damage on the equipment and reduced reliability. But more in terms of short-term, you have heat rate issues and increased O&M and training requirements. So as far as you account for those aspects, you can cycle any unit. There's also some training and education required, which is, well, what kind of component damage exists on the unit. So you need to understand, one, what is the current state of equipment damage on the unit. So just because you've run base load for several years doesn't mean that you have no damage. You've actually consumed a fair amount of creep life on your superheater, on your reheater, some of the high energy piping, even your turbine. So there is some amount of damage already accumulated. The next thing you want to understand is what is the rate of accumulation. So if you take a relatively new unit, but it has been cycled 50, 60 times a year, that is very different from a unit that is run base load. So rate of accumulation is important. And then total damage prior to the failure. So how much total damage do you have on the unit? So all of these things have to be taken into account, but again, all units can be cycled. This is a very general definition of cycling. I know we've been using the word flexible generation and cycling for a while. I'm on slide 25. But so if you define cycling, we would define it both in terms of load following, mild load follows, all the way down to significant low load operations. So, then under it says 55% low load, that is also cycling. And if you're just doing AGC of 5 or 10% change in operation from full load down to 85% load, that is also cycling. And then you have the hot, warm, and cold start, which a lot of us are very familiar with. These offline hours are, for example, so if you have a smaller coal unit, sometimes those definitions might be different. If you have a gas unit, those definitions might be different. But those are just for example. In general, the bigger the change in temperature on your equipment, the more the damage on the equipment. So cold starts are far more damaging than warm starts, which are damaging than hot starts. And my colleague, Doug Hilleman, always says the trick to reducing damage is to keep hot things hot. And so, what is important is that if you're doing load following, the amount of damage that you put on the unit is significantly lower, in fact, magnitudes lower than if you were starting and stopping the unit. To give you an example, you can probably do 50 or 100 extremely low load operations. So not 55%, but I'm saying 30% or 40%, depending on your coal quality and your burners and things like that. But if you're talking units in the US can go down to 25% or even 10% low load, that is still less damaging than a single hot start. So load following is the least damaging, cold starts being the most damaging. And if you're pressing baseload units into cyclic operation, these are some of the things you want to keep in mind. Number one is cycle chemistry. For the most part, when we went to India, there was on-site cycle chemistry personnel. They had good equipment, or at least had plans for good equipment. Having said that, there were, so far in the multiple years that the units had been running, they didn't, some of the equipment was missing. So hopefully in the next few years, if you're performing flexible generation, you need to have a good chemistry program and good monitoring program to go with that. If you have mixed metallurgy on the units, that is going to be a problem. So if you have copper in your condenser or your feed water heaters, if you're performing cyclic operation, that will be a problem in the future. So there are plans to get rid of that. So cycle chemistry is a critical component if you're performing cyclic operation. The rest of it is mostly associated with thermal fatigue. So you obviously have thermally induced cyclic stresses. Again, if you do a cold start, that's the most amount of stress. If you're doing a load follow, less stress. Extent of fatigue damage, and then nature and frequency of the transient. So again, that's what I'm saying is that you can do hundreds of load follows. That's one type of cycling, or you can do 10 cold starts, which is a whole different damage mechanism. You also have to look at thermal grading on the components. So ramp rates on thick section components, your headers, your drum, are far more critical than if you were looking at water well tubes. So thermal grading of the components, so what happens to a valve is very different than what happens to a water well. So you have to manage that. Material properties. If you have older units, typically you do not have P91 in your boiler. That's what we noticed, at least in the Indian case. But if you have a lot of P91 wells, then you have to think about how are you going to manage that part of your system. Obviously, you have to look at material strength, and generally damage is difficult to identify, especially if you've not had any failures. So something on the chart that I have over here is the typical SALI chart. If you have a steam turbine book in your control room, you'll probably see this. And really what we're talking here is temperature change, the delta T on the x-axis, and the rate of change, the delta T over time on the y-axis. And it just shows you the reduction in life of a component based on the rate of change of the temperature or the range of temperature. So you can, think about load following is actually lots of fast changes but small delta T. So that is less damaging than if you're doing a cold start, which is a large delta T. And you can still do a small rate of change, but that can actually cause a lot more damage. Just quickly, creep. Creep is time dependent. If you're running a unit in base load operation, you've consumed creep life. Fatigue is just that. You're changing load constantly, on and off or load following. And then there's a concept of creep fatigue interaction. So if you have a unit, and I can probably show you, this ASME curve on the right-hand side, what this curve sort of says is that you have a nonlinear impact. So if you have a much older unit, if you have a 15-year or 20-year-old coal unit, and you add fatigue cycles to that, the rate of life reduction accelerates. That's basically what creep fatigue interaction would tell you. I'm going to skip some of those charts, but here's a really interesting chart. These are 10 units, and I'll just briefly talk about it. The x-axis is years. The left y-axis is the forced outage rate. The right-hand side y-axis is the total cycles on the unit. And what this chart is showing you is that if you look at the dashed line in black, these are the annual cycles. So when these units are younger, you can increase cycling on the unit, and you don't see an immediate impact on reliability. In fact, there's a 7-year time lag between increased cycles and loss of reliability. But as these units get older, this time lag between increased cycling and reduced reliability starts to reduce. So it's sort of reflecting the creep fatigue interaction discussion that I just had. So if you have a unit that's been subject to creep, then you have, and then you add fatigue cycles, then you have some kind of interaction between the damage mechanisms. Also, one thing to keep in mind is that there is always a time lag. Just because you cycle your units today or tomorrow doesn't mean that you'll have a failure next week. You can have it, there's a likelihood, but it's unlikely. Generally, there's a lot of time lag between increased cycling and then damage. So that's a point to make. Effects of cycling on efficiency. So we all understand if you run a unit at low load, you're less efficient. At the same time, if you cycle a unit excessively, there's also a long-term impact on heat rates. So typically we say that you can attribute 1 to 5% loss in efficiency with cyclic operation. Now you can get all of this back if you do a good boiler overhaul or a turbine overhaul, and you can get some of this heat rate loss over time. But if you're not on a base load unit, some of the units that we visited in India, there was quite a lot of time between turbine overhauls. So you will continuously lose efficiency over time until you perform one of these overhauls. There's also, even though I said that there's a time lag and that there is increased damage, there's also something to keep in mind is the high impact, low probability event. So throughout history, we've seen this, is that as you cycle units, your likelihood, your probability of having a big outage goes up. And the one that I want to point out, obviously, we've seen piping failures on the Mojave unit, the hot reheat line, or the Detroit Edison unit. But more recently at the Boardman station in 2013, this was a hot restart on the unit. And, you had, significant water hammer issue on the cold reheat piping on a hot restart. So you would not have seen this if you were running these units base loaded, because you don't do that type of operation very often. So these are some of the risks associated with excessive cycling. So here's some damage mechanisms. I suppose you will get access to this slide deck, so you can take a look at this later on. And there are more mechanisms and locations. I don't need to go through each one of these. If you have specific questions, you can come back to this slide. So I did mention that depending on the location or the equipment, you have different damage mechanisms. So if you're looking at cycling impacts on boilers, you have to look at boiler seal degradation, tube rubbing, hot spots, drum humping or bowing, and this can happen as you cycle units on and off. You can have furnace subcooling, you can have expansion joint failures, you can have superheater to reheater flexibility failures, DMWs, dissimilar metal welds I've already mentioned. You can have burner refractory failures. That's one thing that we definitely look at when we're walking down a unit, that you want to look for refractory failures. Further down, in terms of electrical control systems, typically if you're running a unit base load, you don't quite see this, but with cycling operation, you do have more concerns with insulation fatigue, control fatigue, wiring fatigue, hydrogen leakage in the generator, fatigue of the generator leads, increased controls, wear and tear. So one thing we've noticed is that sometimes, a $4 or $5 relay, constantly fatigues, causes a forced outage that might cost you, hundreds and thousands of dollars. So, even though, if you ran that unit base load, you wouldn't have that problem. That's just an example of how cycling can impact even something like a control system failure. And not much is sort of immune to additional cycling. If you look at turbine, you have to worry about steam chemistry, erosion, corrosion, last gauge blade flutter. So we recommend a lot of units to consider sliding pressure operation for low load operation. But on the flip side, you have to worry about the Wilson line movement. That's another thing that you have to worry about. So we mentioned water induction to the turbine. That's something to consider if you are looking at sliding pressure operation. You also have steam chest distortion, rotor stress increases. So there's a lot of possible concerns to look for if you're running these units in cyclic operation. So in terms of countermeasures, and this is something that we've been discussing with the units in India, is that if you look at this chart, what we have here is on the y-axis is forced outage rates, and x-axis is the number of cycles. So if you've designed the unit for cycling, and there are certain things that you can do if you're building a new unit, is that if you design a unit for cycling, increased cycling does not impact reliability as much as if you have a base load design unit. So that's something to consider. But even small design components or countermeasures that you might include in your unit can have a much more dramatic effect. So you can see the units in the gray in the middle, where you can, if you have certain design features, you don't have that same forced outage rate impact as you see on base load unit designs. So here's a quick survey that was done a long time ago, and I think it's still fairly accurate if you look at it. So on the left is example improvements in minimum load after operational and capital retrofits have been included. So let's take an example of a 880 megawatt unit, and you can see that at some point the minimum load was 40%, but it was brought down to 28%. That's on an 880 megawatt unit. But if you look at in terms of the ramp rates, you can see both in subcritical and supercritical machines, you can have significant improvements in ramp rates with operational and capital retrofits. Now, in terms of cost-benefit analysis, you have to look at, and this is something that I mentioned in the beginning of this discussion, was you need to determine what is important to you. So you have to examine the aspect of flexibility that will result in the most production cost savings. So is it low load, or is it faster startup? So here are some examples of cold retrofits that can be considered. Obviously, the biggest bang for the buck, if you were to ask me if you only had one thing you could do on your unit, it would be controls and monitoring equipment. That would be the best investment from the beginning. The next best thing that you would invest in, depending on your situation, would be, flame stability is a big concern if you're running units at low load. So, burner upgrades or burner modification. But even before that, you want to take a look at your dampers, your links, your expansion joints, and make sure everything is operational. So you want to look at flame detection upgrades. You want to remove dissimilar metal wells. You want to install automated boiler valves. You want to look for corrosion fatigue. And you can reach out to the Deloitte team or the GTG team, and we can send information regarding where and how to look for corrosion fatigue. So both in terms of instrumentation as well as taking water well samples for that. And then you want to look at variable speed drives. Obviously, in terms of chemistry, look at condensate polishing system. And then, in turbine improvements, you want to look at shell heating blankets, water induction protection, and then turbine seals. So we've given you some here, cost to install in millions of dollars of various retrofit options, and you can take a look at some of these. And both for small and large subcritical units as well as supercritical units, and then the expected benefit of doing any of these retrofit options. And there's a lot of discussion here on gas igniters and dual fuel burners. Now, we understand there are some constraints depending on where you are, but there is enough information here. There's also a reference at the bottom which you can probably Google and download for more information. I'll quickly touch upon, I have 5 more minutes maybe, or maybe a couple of minutes, but here's my point about any unit can be cycled. These are 480 megawatt subcritical coal units that did 2 starts a day. Sometimes, but often, so when Anuj mentioned 2 shifting, these were units that were doing that. Not only did they do 2 shifting, they were also able to do low load operation down to 90 megawatts net, and sometimes down to 60 megawatts up to 6 hours. So, when we go on sites, people say we've done low load tests. And I always ask them, is the low load test for 30 minutes, 1 hour, or 6 hours? Because they're 3 different things. So you can always run a unit down to minimum load for an hour or so, but then things to start to change. So you want to prove out low load operation for up to 6 hours at least to see where are your problem areas. And this unit provided AGC control. So with that type of operation, so in 35 years, about 1,800 starts, it did have boiler tube failures. It did have cracking in DMWs, did have turbine damage, had re-wedging frequency, increased re-wedging frequency on the generator, and sometimes had forced outage rate up to 30%. So that is the impact of doing 2-shift operation on these units. Now, I'm not saying that if you did 2 shifting, that's what will happen. It depends on how much money you spend. So if you look at the retrofit modification that this unit performed, number one thing they did was operational modifications. Now, in terms of physical modification, they added metal overlays to water walls to minimize oxidation, modified the buck stays. So that was one thing. Replaced the dissimilar metal wells, especially for major headers, and then strategically replaced the corner tubes. And that didn't cost them that much money, but it was spread out over multiple outages. In terms of pulverizers, they converted the water deluge system to steam inerting, and that is a big deal if you're going to do a lot of on-off cycling, because you can have pulverizer puffs or fires, and that's a safety issue. In terms of turbine, they added drains, upgraded the lubrication system, modified the vacuum pump. So there was a lot more things that they did on the turbine. The one thing I don't have much time, but we've seen a couple of really catastrophic failures on the non-return valve. So inspection of that during outages is critical. And then, constant monitoring for the generator rotor as well. So here's some more examples of what you can do for improving flexibility. And there's plenty. So if you're doing a low load test, you want to look at lowest safe operation, best burner configuration. Look at variable pressure operation. Look for thermal fatigue risk on the economizer inlet header. You want to look at turbine exhaust hood temperature characteristics. So there's a lot of things that I've listed here that hopefully you'll get an access to the slide. The final thing that I'll spend a minute or two is, so you have all this damage, so what? So the number one thing you want to do is find out what it costs. And so to do that, you want to look at if you're looking at the total cost of cycling, it includes the increase in maintenance and capital spending, the increase in post-outage costs, the long-term heat rate impacts, the operational heat rate impacts, the increased auxiliary power and chemical requirements, fuel and manpower costs, the cost of life shortening. So that's sort of the equation for the cost of cycling. And you want to make sure that you can utilize this cost of cycling, whether it is part of your budgeting, so you can prioritize spend not based on how you used to operate, but how you will operate in the future. What kind of information you need to give your system dispatch and planning so they can utilize this cost. They might have a market opportunity to cycle you and still make money, or if they can understand what it costs and reduces life, that they can make other decisions based on that. And then also in terms of plant operation, if you know your costs, your operators are going to be more careful about using excessive temperation or force cooling the boiler. Those kinds of decisions would change based on what your cost of cycling is. Also, most importantly, the regulatory bodies will understand that having to force existing conventional units to perform two shifting or low load operation is not free to do. You can have real consequences if you forced all conventional units to perform excessive cycling, that you can actually have reliability issues on the grid in the coming years if you don't compensate them. So there's a lot more education and use of this cost of cycling information. Here's a typical flowchart of how we perform this analysis, and something that we did for all of the 4 Indian units. And we have a lot of these costs, and I'll mention that in the end, but each unit is a little different. In fact, when we did the studies in India, every unit had their unique circumstances. So you have to look at past maintenance, you have to look at equipment design and manufacture, vintage of technology, turbine design and pressure, the size of the unit, the age of the unit, time between outages, what frequency of overhauls did you have, what kind of redundancies do you have 100%, can you do 100% bypass, can you do 25% bypass? So there's a lot of different configurations that a unit might have, and each of these things can play into the equation of what does it cost to cycle the unit. So we've got a link here, and these are typical costs of cycling based on the size of the unit and the cost. But you can see there's a big scatter, and we saw the scatter even in the 4 units that we studied in India. Each of them, some units had bad luck with cycle chemistry, so even though not directly impacting the cycling operation of the unit, but because they had bad chemistry, they were forced to shut down the unit more often than they should have. So that causes a different type of cycling cost than if you were a 30-year-old unit that was running base load. And so in conclusion, I'd like to say that, you want to educate plant operations. So you want to look at your startup and shutdown protocols, determine whether force cooling is for economical reasons or to accommodate the maintenance staff. You want to avoid force cooling typically. You want to do more monitoring and inspection. In terms of maintenance, because you're starting and stopping the unit more often, there's actually some opportunity to do some repairs while the unit's offline. But you also want to be smart about, installing thermocouples and monitoring condensate accumulation. Certainly, you want to inform system dispatch about what happens, renegotiate contracts. We've seen that happen, in Europe, in North America, and in Australia, where we've done work where if you have an existing power purchase agreement that has been renegotiated, if you're not running baseload like you did before, certainly, in terms of new construction, you want to keep in mind, do you want a baseload unit or a cycling unit, because that can have a big impact on how you design the unit. And one final thing I want to say is that some of the work that we've done has been taken much further along. So the GTG team, Anuj Ripu and Mr. Sinha, from NTPC, have led some of the work that we've done and actually gone to the government of India and issued this report, and I'm sure they can share the links to this report. So of all the work that we did, it's actually having some real policy output from that. So with that, I will take a pause and open it up to questions.
Thanks, Nikhil, for the informative presentation. We have a series of some really interesting questions that have come up from the participants. I will start taking up these. So first question that we received from Anindya from Tractable. The question was, are the power system studies carried out by USAID, and are these publicly available in any link for the pilot projects? So let me answer this one. So the power system studies under this particular pilot, so this is essentially comprised of the feasibility studies at the couple of units at NTPC and Ramagundam. These were carried out by GTG RISE through support from Intertech, and the financial support was obviously being given by USAID under the GTG program. All information all relevant information related to not only this pilot but the other pilots that I mentioned earlier, those are available on the website www.gtg-india.com. We will be sharing this link as well with all the participants, those who have attended. So that's the first answer. The second question is from Deepak from WRI India. Deepak asks that how do the flexibility recommendations for GSECL and NTPC units fit in with the emission norms specified by MOEFCC? And I think there is a continuing question from Deepak that can these flexibility changes also coincide with the 2022 deadline for emission norms? So I would request Mr. Sinha as well as Nikhil to take this up. Mr. Sinha, over to you.
Yeah. Can you hear me?
Yes.
Yeah, good morning, everybody. Before I start, I'll give a brief introduction of what are the work that we did and also answer some of the questions. Like one was the report that was done for CA. The last slide that Nikhil was showing. Many of the answers you'll find in that report. For 2022 scenario, what would be the requirements for India? What would be the requirement for coal plants? What would be the flexibilization requirement, and how much it would be required to flex? Like from the afternoon to the evening, there would be a requirement of around 82 gigawatts in the Indian scenario. And all the flexibility sources from like hydro, gas, they were all taken into account, but still coal would need to flexibilize that much. And again, coming to your question on how do the flexibility recommendations of GSECL and NTPC fit with the emission norms? See, whatever flexibilization that we are doing will ultimately add to the renewable integration. The amount of renewable that we add into the grid will depend upon how much the coal units flexibilize. So the net emissions will reduce. The more RE that you add into the grid, system-wise emissions will reduce. So that way it will help. If you're asking from the perspective of individual unit, then it would be a different story. Because emission norms will have to make more effort to meet them, especially for like SOX. Already equipments have been installed, and operating those units on lower units, they will require different interventions. And coming to another question, can these flexibility changes also coincide with 2022 deadline of emission norms? Flexibility and these are not together for unit-wise. Unit-wise norms, like ESP, particulate emissions, they'll decrease if you burn lesser quality of coal. Then that will decrease. That way the emission norms can be met. But for your SOX, NOx, the performance of the equipment that you install, for low load, they'll need some more interventions. And then another question, what are the present regulatory view on flexibility of plant in India? Are existing plants cycling to absorb variable RE? Yes, definitely. But there are other reasons also, like coal shortage. In the past year, coal shortage has been one reason for cycling of the units. So all the units are not cycling only because of the RE, but like there's reduction in the curtailment of RE. That only tells you that coal units that they are taking care of the flexibility needs and for the RE integration. Yeah.
So
right.
that
if
was
I can, if I can add.
Yeah, you can please.
Yeah.
All right. So like Mr. Sinha mentioned, one thing is that, and I think the other theme of even this document that I'm sharing is that the flexibility retrofits cannot be implemented throughout the fleet. Not every flexibility countermeasure or retrofit can be applied to every unit. So that's one thing that we should keep in mind. There are certain things that will apply to all the units, but there are not all options can be applied to all units. There are some operational constraints with having emissions controls and low load operation, as well as startup operation. So we have some units in that we've seen. If you have bag houses, that if you're operating at extremely low loads, that you can have dew point corrosion and other such constraints that can occur if you have emissions controls installed on the unit. So that's one part. So I think part of this analysis in the future would have to include what are the operational issues that you will encounter once you have emissions control technologies installed on all units. The other flip side to this equation that Mr. Sinha alluded to is that as you have to improve the flexibility to increase the amount of renewable penetration. Also, in terms of the total emissions output for the year, for example, might go down in terms of operations of the fossil unit. But the net emissions per megawatt hour goes up as you perform flexible operations. So one, if you are starting and stopping a unit more often, you are going to emit more SOx, NOx, and CO2. If you're running the unit at low load, you're going to emit more per megawatt hour. So on a per megawatt hour basis, emissions goes up, but on an annual basis, if you're not running this unit, as Mr. Sinha said, you're going to have less emissions. Thanks, Anuj.
Thanks, Nikhil. So I will once again take up the question from Atul Mudaliar from the Climate Group. So Atul asks, what is the present regulatory view on flexible core plants in India? Atul, we mentioned that existing norms cater to the compensatory mechanism being provided to plants. running at technical minimum of 55%. So the regulatory norms are only allowing up to 55%. There is no compensatory mechanism available below, if you run a unit below 55% as of now. There have been instances where states were required to back down due to increased RE penetration. We have similar specific examples from South. That's your next question. Are existing plants cycling to absorb variable RE? So yes, they have started doing that, going below 50%. In fact, some of the utilities, we have examples from Karnataka, which have actually realized that those additional costs are not being reimbursed as of now, and that specifically creates a requirement to develop a framework for compensatory mechanism, and this is precisely where we have submitted a regulatory note to CERC based on the damage cost modeling studies carried out with support from Intertech under this pilot. Your next question is, are new plants in India being designed with a view of flexibility? So Sinha sir, would you like to take that up?
Yeah, the previous question, I'd like to add. Like in India, many of the states, they are not going below 70% for different reasons. And the compensation is there for 55%. Even many of the states, they are not compensating. And compensation, today it is only for heat rate. For your damage and your increase in wind-up cost, like due to your light consumption, that is not there. In fact, nobody knew it and nobody had the numbers till we carried out these studies in 4 units, 2 NTPC and 2 at GSECL. So that numbers we got, and we accordingly presented it to the CRC. There's a concept note that has been submitted to CRC, and that will complete the whole compensation mechanism. Other part is going below 55%, because in the CES report, the primary requirement will be for reducing a minimum load. So units will be have to decide to what level to operate. Another part, like all the units won't be able to go at 40% because of the coal. There's a lot of variation in the coal quality in Indian context. Some units get very poor coal, where the specific coal I've seen is 1.2, and somewhere you get very high grade of coal. So the unit selection has also to be done. There has to be different criteria for selecting the units, like with which unit, what you want to do. Every unit will deliver a different value to the grid. So that's it. And what was the next question?
So the next question was is from Atul again. So was there any assessment on quality of coal that affects the ability of a plant to cycle? In India, the coal isn't of very high quality and very inconsistent.
Yeah, Atul. We carried out a couple of test runs, one in Dadri and recently at NTPC Mahodar. Both have different grades of coal, and we achieved 40%. And other test runs also has to be carried out. We had also attempted a test run at one unit, Talcher, Kania in Odisha, where a very bad grade of coal is supplied. There the coal was, specific coal was around 1.2, ash content was 55 to 60%. So there we couldn't go below 60%. So those units will require different kinds of intervention. See what, as Nikhil pointed out, like one is any unit can be cycled. It's only the cost that will vary. You'll have to spend more if you want to cycle these types of unit of like Talcher, Kania. And is it cost effective, or will you be able to recover that cost? So that is why you need to select the units. Other part is flexibilization in that unit is one part, and flexibilization in the coal supply. That also would be needed. Like in an Indian context, you need to do some coal blending, and you need some stock, which is definitely challenging. So with this coal in the Dadri, actually we are planning to install coal analyzers online and coal measurement, because there's a lot of variation of coal. You get coal from around 12 mines. There's a lot of variation. So how will the operator know, like when he's operating, you may have different grades of coal in different bunkers. So which coal comes at a particular point of time that can alter the operation. So for that, we are installing coal measurement, coal quality and coal analyzer, which will give feedback to the control system. So what of these interventions required?
Thank you, sir. Thank you, sir. We have another question from Anup Punia from the Climate Action Network. The query is, India's coal fleet is relatively younger, with 20 to 30 years still left with many plants. So can we say that the coal fleet is well placed to handle the flexibilization in the next decade when 200 gigawatt RE comes into play? I would request both Mr. Sinha and Nikhil to take this up.
Yeah, I take up. See, in India, one thing is, first thing first, we need to have a compensation mechanism and incentivization model to ensure proactive participation of these units. Like states, they are reluctant to come out and do flexibilization. Again, there must be some ways devised to recover the cost. And all the key policy makers and regulators, they are on one platform. They want it. And NTPC is also very proactive in doing it. Every day, like some unit test run is going on, and 55% all the units are operating, and very soon it will go down. And in the first place, like operational practices, if it is modified, then very easily we can go up till 40%. That way we are well placed till 40%. And if you are required to go below that, then we need some retrofits, some even costly retrofits. So just with operational modifications, lot can be done and lot of legislation can be achieved. Yeah, Nikhil, do you want to add?
Yeah. So yes, I think the average age of a unit, on a large sample like India is should be qualified. So obviously we have some units that are younger and some units that are older. So you have units like Jhajjar which are around 10 years old, and then you can have some units that are 35 years old. So that's one thing. But power plants are like humans. It depends on what they have done in their past. So if they've exercised, eaten good food, they're healthy, then they can do all kinds of things in the future. So I think that applies to these units as well. If historical operation of the unit and their maintenance, their operating strategies prevented the unit from having a lot of damage, then yes, they can perform a lot more flexible operation in the future. But on the flip side, if you have not taken care of your asset, then you are not able to perform all that much of flexibility. Mr. Sinha, would you agree?
Yeah, very true.
Okay. So the second question from Anup is, the 40 gigawatt coal fleet is spread in the country and financial is easily available. So would the government need to create a scheme or a fund to keep some of the coal fleet afloat? So now, would you like to take this up?
So, Anuj, I don't know if that is something that the GTG program would say yes or no, right? I mean, I think that's that's to have a separate fund to keep coal plants afloat
we will not be able to. Presently, we are not in a position to commit on development because every unit, as we found out since first modeling studies, every unit is unique in its design, different from other units within the same stage, same plant. and that require separate studies what kind of retrofits are required. But we said that regulatory mechanism in place for low load operations below 50% would definitely recommended. We are looking forward to the national regulator on taking this up on priority. We expect that in the next course of 5 or 6 months, there would be a mechanism in place with a change in the existing regulations to support operations. Right. The next question is from Vande from Kosovo. I think we answered to this question. The question is the existing compensation mechanism provided by CAFC for part load operation, start stops and cycling good enough? If no, what could be a sustainable compensation mechanism for better flexibility response from generating stations? Hello? Nikhil, am I audible?
Yeah, there's a lot of echo, so I couldn't hear you.
Hello?
Okay.
Yeah, I'll answer. Yeah, in the present regulatory compensation mechanism is compensation only for heat rate. There is no compensation for start stop except for oil, and that too and after 7 starts. So that is what we have put in the regulatory concept paper.
Right, and just to give some context now that I understand the question, so
we hope it would be sustainable.
Right, so just to give you a global view on that question, now that I understand the question, different. So in some cases there are compensation available for ramping. So if you have ramping constraints, then there are some incentives that have been put in place globally to provide incentives and payments for fast ramping, both upwards and downwards. And then in terms of startup, there are some global case studies where the regulatory body will compensate, again, very similar to what Mr. Sinha said, where up to a certain number of starts there is no compensation, but beyond that there is. But there's even different compensation for the type of start you do, and not just for fuel-related startup, but also damage caused from cycling operation recovery, cost recovery has been given. So if you look at globally, our expectation is that even in India we will be able to develop these types of mechanisms for cost recovery.
Right. Thanks, Nikhil. The next question is, what has been the experience of cycling in nuclear units? And can we provide any reference to any published literature on this? Nikhil, if you can answer this question.
Yeah. So Anuj, I will send you some links that I can probably share that with you. We've been working with the International Atomic Energy Agency in Vienna on looking at flexible operation of nuclear power plants, as well as some specific case studies in the northwest of the U.S. and the east side in Canada. Generally, nuclear plants are not going to do start-stop cycling, both from a safety standpoint as well as operational constraints. You cannot do that. However, nuclear units are capable of providing some amount of load following. So if you want to take a look at Bruce Power Station in Canada, which is owned by or operated by Ontario Power Generation, they've implemented a retrofit where they dump the steam into the condenser So you take a what I would call a heat rate penalty by doing that, but you do provide flexibility. There are some other units. So that's simply not many people have done much with the fuel cycle, but there are other ways of performing flexible operation. But again, we have never seen a nuclear unit performing on-off cycling. It's mostly load following, which has been done successfully on some sites. And I'll share a couple of links with the GTG team for them to share with the audience.
Thanks, Nikhil.
On the cycling of nuclear units, this was discussed in detail in CA, the CA committee. In fact, we have a very small capacity of nuclear, and it was decided that we don't need to cycle them because it won't make any significant difference. So why to take that risk? And even if it is to be done, it will be on a very small load following mode. So then in the report it came out that nuclear will run on base load and no cycling will be done. So that has already been decided. And we are not going to do cycling in nuclear in India.
Thank you, Nikhil. Thanks, Mr. Sasana. Next question is from ANS Surya Narayana. It says, in one of the slides it is shown minimum load achieved was 28%. The question is that in case of supercritical units at this load, it runs in wet mode. Now, while ramping up from this load, have you studied the damage effect of change from wet to dry mode? And while ramping up, how taking a new mill is being taken care of, either in auto or manual?
All right, I'll let Mr. Sinha start with this discussion, and then I'll add to that. But just for the GTG program, we did not look at supercritical units. It is true that you will have the transition, but I'll let Mr. Sinha comment on that, and then I'll add some more details to the example.
Nikhil. This is one area which we have to conduct studies in India. In nuclear, we haven't conducted any study. And presently, we are doing only load following. So with lot of experience of Europe, we need to bring in something here also. Because in NTPC, many of our supercritical units, they are all far away from the mines. So they are very low in the merit order, and they are likely to be flexibilized. Then we need to flexibilize them because the cost of energy is very high. But we are not doing it here. Like start-stop also, it's difficult. So we need to study them also. At least one pilot is required somewhere for supercritical.
Nikhil, would you like to add?
Yeah, I think again, what I'll do, Anuj, is that I will send you a couple of references where we have looked at supercritical load following at 20% min load up to full load. Now you have significant reduction in ramp rate capabilities of the unit. Also, there were some particular retrofits that were looked at, not just on the boiler side, but also on the turbine in this particular case to avoid water induction issues. So I'll send a specific document that you can share with the audience so they can look at the supercritical load following.
Right, sure, Nikhil. In fact, I received one of your documents right away. So we'll be sharing those with the audience. I think we are done with the questions. If there are any further questions, please feel free to write on the website www.gtd-india.com. Also, we'll be sharing you our email IDs for any further queries with Mr. Sinha and Nikhil. Thank you once again for all of you to join. Thanks, Nikhil. Thank you, Monali. Thank you, Mr. Sinha. Ripu, would you like to add a few concluding remarks?
No, thank you. That's great. Well, I must say that it's overwhelming to see a great of the greening. I can see that we are already well past our stipulated time, and we still see most of the participants on, and it certainly encourages us to conduct the second webinar in the series, which from the comments and questions we see will be on the regulatory compensation framework, including the assessment of damage costs and identification of mechanisms for supporting flexibilization in the coal-fired power plants. We will certainly keep you posted on with the recording of the webinar, and sorry for not able to take any further questions. We are already well past, almost half an hour ahead of past our stipulated time. We will certainly answer queries. If you can email us all the queries on the communications@gt-india.com email ID, and we'll certainly keep everyone looped in and communicate the further dates for the second webinar. Thank you so much, and we really appreciate the time of all the participants. Thank you very much.
Thank you.
Thank you.
आपका आवाज इससे जा रहा था, आपका आवाज उससे जा ही नहीं रहा।